Right. So the first thing I'm going to do for you guys is you don't have permission at the moment to go into the Year 12 folder. So I'll create that permission for you so that you can get into it.
Have you decided what option topic we're doing?
No, not at all yet.
Do we decide that?
No, we'll wait for a little bit. There's no rush on that particularly. The only reason there's a... Sorry? You've got term 2, term 3, and then you start term 4 as the exams. Although physics is often in the latter part of the exams. Yeah, not just randomly, only when I normally had physics. Okay, so at the moment, even though I've done the daily work summary for you for yesterday, you probably can't get to it because I can give you permission to this folder. So I will give you permission so you can do your work on Thursday, Friday, Monday, Tuesday. And I have booked laptops for those people who don't have laptops, so they will be in here for those lessons. Now, yesterday we were looking at this document, which is a document I lifted from that scientist I was telling you about, JSD, John Denker, who actually has got quite a presence on the web if you go looking for his name and see what he's done. And it mentions that he was a chief, he's actually a division research chief at Bell Labs before he went to Caltech and did other things around the place and became a chief researcher in one of the research divisions in a major university. And his expertise includes things like computer software, computer security, communication and neural systems, physics of all sorts.
These first thoughts coming up with this John
Denker, D-E-N-K-E-R. Right. But he's quite a particular man, also quite crazy. Anyway. Yeah, they seem to be. All right. So yesterday we got to this part, which where it talks about where most people live placidly near the Earth's surface of the Earth, where to a good approximation, the value of g, that's the acceleration due to gravity, little g. Now never forget that. G is not gravity. Little g is the acceleration due to gravity. And it's the local acceleration due to gravity.
So what is actually, like if you wanted to express gravity instead of acceleration due to gravity, that's big G, but what is...
No, if you want to express it, gravity is a force, so as he showed earlier on the board, you could express it as F with a little g underneath, or there's a whole variety of ways people do express it. Big G is another constant in physics. It's actually the universal gravitational constant, which has its own value. So if you wrote big G down, meaning gravity, they would confuse people no end. So yeah, it's the way you typically would with an F with a little g. Now for most people living their normal lives, variations of gravity don't, the acceleration due to gravity, or the force that we experience, really do not matter very much. Because the variations are so small, it doesn't affect what we're doing. Okay? So that for us, if you thought about the Earth as a perfect sphere, and you did some theoretical measurements, you could say that on that sphere, the thing called the geoid, which you don't need to know the name, but it's just the name that we use, 9.8 metres per second would be the acceleration at sea level. That's fine. And in our course, we treat the acceleration due to gravity as though it is that number. But just be aware that it isn't that number, except by fluke. Yeah.
In this space topic, the assignment that you're going to give us, is that going to be a research assignment or a practice?
The first one, it mirrors last year. So the first one's a research, the second one, I think it's test, the third one.
You mean
last year 11. Right. When I was doing geophysics, this mattered, this stuff, because we used to measure gravitational attraction due to the planet, and the instruments I used are sensitive, or used back then, was sensitive enough that I could tell the difference in the acceleration due to gravity from the measurement on the floor to the measurement on the chair. Okay, we worked in milligauss, very, very small units, and it was sensitive enough that it would pick up the very small change in elevation. 0.5 metre is enough to get a different reading. So the further you are away from the centre of the Earth, you'll get a change in the force.
Sea level is where you get that 9.8.
Yeah, Absolutely.
What
But
about your
it gets
core?
it gets stronger, but that's where we measure it from, right?
Don't forget, all right, moving towards the core theoretically makes the okay, if there wasn't any other planet, you just went to a smaller planet, then that wouldn't be 9.8. It depends upon the density of the planet, all sorts of other things.
Yeah, but if you went
But if you dug into the Earth, don't forget,
gravity gets stronger.
not necessarily. Because don't forget, you've got a whole lot of planet above you now that's attracting you outwards, as well as the part beneath you attracting you inwards.
In that case, if you
And
measure
so-
from the surface, shouldn't they really take the average, like, of the height on Earth? So the not
When you get concerned about it, for us, 9.8 is fine. And what they imagine to get that is that the Earth is its average diameter of 6,360 kilometres, and that that it's all made of water. That there's no tides or anything else, so that the water sits in a nice uniform sphere, and that gives you a level to work at, right? But in practice, that is not true, and this is what this stuff's talking about here. The weight of an object, the force due to gravity, will be very slightly time dependent for various reasons, including weather-related changes. So in other words, air pressure will change the weight. Higher air pressure will push down more on you, which make your weight go up. Low air pressure, yeah. But the instruments,
Weight just change the weather.
the instruments we have is not that you have in your bathroom are not sensitive enough to notice that. Right, you need really sensitive instruments. Also, where you are on the Earth's surface would change it slightly because the Earth rotates. And so your centripetal force acting on you is slightly different at different parts on the Earth. That's going to change your weight. You also notice that it says it's time dependent in other ways. For example, the shape of the Earth changes during the day. So that when we get to midday here, we will be elevated between about 2 and 3 metres compared to where we are at night. Because the Earth's crust actually flexes with the passing of the sun over the top of it, over the top of us. We also find that the position of the sun over us will drag us upwards slightly with its own gravitational attraction, and so it slightly lessens acceleration to the Earth.
The whole Earth is body process, it just pulls a little bit of.
It actually flexes the crust slightly,
Could it do that to
and
a
it's what's
solid
called
rock
earth tides.
like Mars, which is just a solid rock?
Yeah, to some degree.
Same.
You think of rock as being really inelastic, but it's not. It does move. The other thing that you talk about is what you're doing at the time might vary your weight. So if you are, and we do an experiment later where we show this, and there's a big discussion about apparent weight versus true weight or whatever, and it's a discussion scientists actually will have. But if I'm in the lift over there and it starts to accelerate upwards, your weight will be recorded as being more. But does your weight actually change? Because if we define weight as the force due to the acceleration of gravity, it's not actually the gravity that's changing, is it? It's the acceleration of the floor against our feet that's changing things, but our scales will change because we're pressing harder against them.
Does that mean that you've got mass and weight? Your mass stays the same, but would your weight change? Or
Can
neither
you
of
do
them
an
change?
example of that, please? Of this calculator?
Okay, look, here's the issue. We define in this course, weight is your mass times acceleration due to gravity.
So it's not.
So that's how we define it. So in this course, if they say, what is weight? You say, it's the force we experience due to gravity defined as W equals mg. That's your answer for the course. What I'm trying to get through to you is that's a neat answer and you can use that. You're fine to use that as long as everyone understands that that's what you're using. But if you're in real life and you theoretically work out what your weight's going to be and then you jump on a machine and measure it, you might get a different answer. And you have to understand why you get a different answer. And then you've got a choice to make. Do I choose the theoretical value of weight, is what weight really is, and call that my true weight, and then say what my scales give me is my apparent weight? Or do I just say weight is whatever I measure when I jump on a machine?
How do you measure your mass?
You have to use, there's some very clever ways using balances. Yeah, I mean in practice what people do to find your mass is you weigh yourself and divide by a gravitational value. That's what they tend to do. But the true way is you get a very, very precise instruments which are balances, not scales, and you get a calibrated thing on one side and you on the other, and you do that.
So mass is measured in newtons.
No. Mass is kilograms, weight is newtons.
So then how come on the scale does they kill you? Just because
Because they've calibrated for Earth and they're actually just, rather than having to say, I weigh 635 newtons, the people just find it convenient to say, I weigh 63.5 kilograms. It's just
It's easier.
easier, and it doesn't really affect us because we don't go anywhere but on Earth, and we're not worried about that precision of measurement. But for us, who get in physics, who get concerned by these things because we're working with very fine measurements and very important concepts, we need to be a little bit more precise about it. And this stuff affects real life physics, things we're working with. So, for example, it's really important in inertial navigation systems and whatnot to understand the concepts about how these forces work.
So weight is, so how would you just define weight in words? Yeah, that's
Well, when I'm working as a geophysicist, the way I would define it is the measurement of the force through a gravitometer, right?
Yeah.
But when I'm working in this classroom, that's my definition of weight. And then when I get there, that's fine. That's okay. I can do that.
So when it says define
As long as everyone in the room knows how you're defining weight and you all agree upon it, then your answers are consistent. aren't they?
So if the question says define weight, you just
Do that. Write that. That's our Year 12 physics answer for weight. But when you go to university, you've got to understand it's a little bit more complex.
What happens if you get a question, define weight, it's like 20 lines and it's a 20-mark question? It's W, move on.
And then you go on and say, of course, this force is dependent upon, and you can have a whole list of things. You can talk, I haven't introduced yet, at the end of this topic, you'll start working out that mass is not necessarily, doesn't necessarily look constant. That mass might change in certain circumstances, and you have to think about the relationship of energy and mass and how you talk about that stuff. And you might talk about how gravity changes. Not gravity, the acceleration due to gravity. Which brings us to the question I want to solve today, which you guys are going to work on.
Does energy have mass?
Yes, because energy and mass are equivalent things. They are different expressions of the same stuff, whatever that stuff is. Now, number 11, the weight will not in general be equal to the total downward force. Weight includes only the force due to the local gravitational field, not forces due to buoyancy, air currents, magnetic fields, bungee cords, or anything else. Okay, so that just understand that weight can be the theoretical value, W equals mg, or it can be a value that you measure that has lots of other forces contributing. And it's up to you to decide how you want to define it and how you're going to work with it, and that will depend upon what you're trying to do. But the base answer to all this is always, whatever you call weight, let everyone else know what you're calling it, so that they are talking with the same language. That's the important part. Everyone's on the same page, and then you're fine. And for our physics course, W equals mg, that's our definition. Right. Hopefully I can close this. What we're going to do is we're going to do an experiment. And I hope it's on here. If not, I'll explain it and then you can do it and we'll write up later. I might not have written it up on here yet because I've actually got it on Moodle from a university page. I've got it summarised out. Okay. The question that we have to ask ourselves then is, what is the acceleration due to gravity in this room? Is it actually close to 9.8 metres per second? Now, measuring it that way is incredibly difficult. The way that we would typically tend to do it is by using one of these things, a pendulum.
Did you see the video of Neil deGrasse Tyson, the massive pendulum that he let go at his chin?
Yes, yes, I've seen that.
What is it? Can we put it on?
Okay, no. So what you got is, there it is. But it wouldn't have.
Not really.
well, it will just
What you've got is a pendulum, and we have a formula which describes the way that pendulums, or the time it takes for a pendulum to swing from there and back again. So it will start here, it'll go across, it'll stop there, and it'll go back again. Now there's some limitations with this method you need to know, right? The thing that we use is the period, that's the time from the start over to one side and back again, equals 2 pi, the square root of the length on the value of g.
I thought that out myself, sir.
So you can rearrange that to find out what g is. It's not too hard to do. And I'll do that in the, for you a little bit later, because I just want you to collect some data so we can do those calculations. So what you need to do is you get yourself a pendulum. What would be a convenient length? Would it? I'd go 100 centimetres, which is 1 metre. Why would I choose that?
Like the length of string.
Yeah, no, have to be careful about that. The length of the pendulum, 1 metre.
That's because SI units is meters, so it'll just be 1.
Yeah, that just becomes 1 in there. It's much easier to have the number 1 in your equation. So let's make life easy for ourselves and use 1 metre.
So do we have to type
So what you need to do is you're going to get yourself a, hang on, slow down. You get yourself a pendulum and you clamp it in place, and then what you can do, not like that, spin them around so they're the right way, and you actually just pull that up and down to get a metre, which is from the top of there to the base of, actually to the centre of the mass. Not the base of it, the centre of the mass. So
just like, say we got this big long one, and can we tie it with a retort stand and like a
put it in the corks like this, and just move it until there's 1 metre from the very base of it to the centre of the mass. Over the edge of the cupboard with a retort stand.
Can we do it on these tables? Can they
Yep,
swing up and
yep.
down?
Now, then what you're going to do is you're going to pull it out, and you don't go any more than about 25 degrees outwards. If you go too far outwards, you actually create little oscillations and things in the system which make it less accurate. So you don't want to be 5 degrees, but you don't want to be 30. You need to be, it's just sort of about that out there.
Or because if you
And then if you go up there, it actually bounces, right? So there is a, with this method, the most accurate method is when you're out about 20 degrees out. You let it go and you count. Now, we're going to let it go for 5 swings or 10 swings. It's up to you for the amount of time. So it'll be 1, 2, 3, 4, 5, and you time that time. Record it. You're going to do that multiple times, and then you're going to get the average of it. Now, the reason we use 5 or 10 swings is really simple. Let's suppose that for 10, it takes 1 second for the pendulum to go from its starting point there and back again. Now, if that's one swing, 1 period from there and back in, and you are a pretty dodgy measurer and you are out by 1/10 of a second, what sort of error do you have in that measurement? It's 1/10 of 1 second, so it's 10% error that would be introduced in there. If you let it swing now for 5 swings back and forward, but you would still have the same error, you're now talking about 0.1 of a second out of 5 seconds, which is, what is it? It's no, it's not 20%. It's 1/10 out of 5 now, not 1/10 out of 1. So it becomes now. If you go over 10 seconds, that means you're going to have a 1% error. So just simply by letting it swing more often, you dilute your timing error.
Yeah.
Just to explain, if a 1.1 of a second. Well, if you always 1/10 of a second slow because of your reflexes, right? If you try and time 1 second, that means that you will record 0.9 out of 1 second, which means 10% error. If you do it over 10 seconds, you'll get an answer of 9.9 out of 10, which means your error is 1%. So you're actually reducing your error by doing that. Okay. All right. So your simple job is 4 or 5, 6, 7, whatever can go. sets of data for the pendulum swinging at 1 metre. I'll rearrange the formula on the board for you, and then we can analyse our results to get our gravitational acceleration.
Yeah.
It's a Monday.
Wednesday.
It's a Monday.
Hey Riley, can I borrow your meter lock rule?
Oh, I don't really want to.
1 metre rules are up there.
Oh, really?
So it's a meter from the end of the centre or a meter from the start of the
What did I say? The centre of it.
centre.
The centre of mass.
So, African. We go again? Yeah.
Hey, sir.
Yep.
Swing back and forth.
Okay, so you got, that means it was 2.012 seconds for one swing. I can just throw that into a calculator so I get, first of all I need to do a scientific calculator. Does this have sine on it? Not sine, pi? That's really annoying.
So, we got 5 swings, 10 seconds.
So
No, 5.
that's that squared times 4 equals, divide by 2.012 squared equals.
Do that again. 3. Can't.
So if I do that, and the other one is 22 divided by 7 equals squared divide by
Yeah, so I got nothing.
times 4, hang on, divide by 2.022 squared equals, that leads to 9.664 seconds. Okay, so that's Marnie's is 20.41 for 10, so 2.041 for 1. And that leads to, I'll do the calculation, clear that, 22 divided by 7 equals squared times 4 equals divide by 2.041 squared equals. What's your other one, Brad?
Yes, that's one. Let's get these cooking.
Whose was this one? So what was your second result?
76
Okay, let's see what you got for that. So that becomes 22 divided by 7 equals squared times 4 equals divide 2 squared equals. So if you get 0.07 divided by 9.8 equals times 100.
Yeah, so I did one with 30. So what's the
The equation, I'll show you. The equation is there. So that's how I've worked it through. All right, year 11, just stop what you're doing. Oh, sorry, year 12. Just stop what you're doing for a minute and listen up. Listening time is an art where you don't talk. Okay, so what I do is I took the equation, I've done the rearrangement for you to find out the value due to G. If you can't do that yourself, you're quite free to see how I've done it there. Then what I did with that is I took people's results and did some calculations. So the first result I was given was for 10 swings of 20.22, which led to acceleration due to gravity of 9.664 metres per second squared. The second one from the Cody's group, they got 2 seconds exactly for the period if they did 5 swings. That gives them a result of 9.87 metres per second squared, or 0.07 away from our theoretical value that we use, which is 0.71% in error. That's a really acceptable error. We normally say 5% is well within the range of what we want. And we've got 9.76 and 9.48, depending on who was doing it. They're all great results. The actual result for here, because we're sitting on top of a great pile of sand and loose packed material from the river, is actually 9.79, lots of different digits. So that's the actual value they get when they do gravity surveys here. Okay, so